Hi guys, here we are discussing about the temperature expansion and Adelius laws. Now starting, we are also known about the everything made of the atoms. This idea was fully accepted about the 100 years ago in a part because of the Einstein analysis of Brownian motion. Brown, who studied the sex life of plants, is the biologist. Notice a lot of the jiggling pollen grains under his microscope in 1827. He assumed it was because they were alive, but later found the identical jiggling with definitely dead stone powder. This was not understood a half of a century. Now, the size and the mass of the atom, it is the some necessary information about the atoms. The hydrogen atom is the smallest and is the atomic number 1 and atomic mass will be is a 2, and if the size is nearly 1 angstrom will be equal to 10 power minus 10 meter across. The others are so also is others are the bigger than this. And now the Avogadro numbers, that means the number is 6.022 into 10 power minus 10 power 23. The number of the atoms or molecules in a 1 gram, in a 1 gram mole in a 24. Avogadro numbers means number of atoms or molecules in a 1 gram mole in a 22.4 liter volume at a natural temperature pressure. And now the atomic mass unit is 1.66 into 10 power minus 27 kg. The mass of the molecule in AMU, that is the mass of Avogadro numbers atom in a gram. The 1 gram mole of water is 18 gram. This is just reminding you. Now the talking about the measuring temperature, we can tell by touch if something is hot or cold, but this is unreliable. The first serious attempt to measure the temperature was by Galileo in 1597. The glass bulb was held thin neck, the end of which is immersed in liquid. As the temperature varies, the gas in the bulb changes volume. As the temperature varies, the gas in the bulb changes volume, sucking up liquid or pushing it down. Now, some clicker questions for you, and not. Why was Galileo thermometer no need for the comparing the temperature from day to day? This is the answer, and giving the answer is nearly 2 seconds. The gas expansion was too small to see clearly. Now, the thermometer. Many thermometers use the expansion of the liquid as a measuring of temperature. You should be familiar with the two standard temperatures scale, that is the centigrade and Fahrenheit. Fahrenheit will be calculated Fahrenheit, and also one is Kelvin, and also centigrade and Fahrenheit, and it converted between them by metallic strip. Two metals with the different expansion rates welded together bend when heated and make very robust thermometers. Now talking about the zeroth law of thermodynamics. If the two things at a different temperature are in the thermal contact, so heat can flow and no heat is being supplied from or being drained to the environment, they will reach the same temperature. They are then set to within the thermal equilibrium. Zeroth law states that if A is the thermal equilibrium with B and B is thermal equilibrium with C, then it must be the thermal equilibrium with A and C. If this is not true, the thermometer would be meaningless. So it will be the true. Now the thermal expansion, how you can get the expansion in the substance by the thermal heat. Now a solid rod will increase in length when heated, typically by order of 10 power minus 5 of its the original length of each degree Celsius. That means if we increase the 1 degree Celsius temperature, then the solid rod will increase on 10 power minus 5 meter of its original length. Now it will be expanded by the some proportion in the other directions too. This means that there will only be a change of 1 part in 1000 over or 1 degree Celsius temperature range. So this increase changes are not visible to the naked eye. Some device is needed to detect them. It is very small. Now talking about the thermal expansion notation. It will be the expansion with the two types, three types: linear expansion, volume, and density. Now they're talking about the linear expansion noted by the alpha. It is defined by the del L upon L0 is equal to lambda alpha into del T. Here del L is the change in the length, which will be the increased, and L0 is the original length, alpha is the coefficient of linear expansion, and del T is the temperature. So here will be get the alpha is the constant. It will be the vary with the some other with the different metals. Now alpha is 1.2 into 10 power minus 5 for iron and 0.9 to 10 power minus 5 for glass. So now alpha getting the coefficient of volume expansion beta is defined. Del V upon V0 is equal to beta into del T. Here del V is the change in the volume, V0 is the original volume, beta is the volume expansion coefficients, and del T is the change in the temperature. Now relating linear and volume expansion. Imagine a cube of solid of side L, volume will be the L cube. On increasing the temperature by del T, the length of each side goes from L to L plus L to L into 1 plus alpha del T. So the volume increases from L cube to L cube into 1 plus alpha del T the whole cube. Now alpha del T is a very small number, so we can written as L cube into 1 plus alpha del T of whole cube will be equal to L cube into 1 plus 3 into alpha del T. Those other terms are really tiny, so it will be the neglectable. Now solids, for the solids, alpha is equal to 10 power minus 5. Recall the volume goes to V into 1 plus beta del T, so beta will be equal to 3 alpha. You can verify this relation with some different manners also. Now the clinical question something for you, and now talking about the different volume expansion coefficients for the liquid. Most organic liquid have coefficient around 10 power minus 3, which is a much more greater, 100 times greater than the solids, and a good reason for not filling a gas tank to the very top. But mercury has a low expansion coefficient for a liquid, 1.8 into 10 power minus 4, is still 20 times that of the glass. Therefore glass mercury thermometer work fine. Thermometers. Now water, unlike almost all of the liquids, expands when cooling from 40 degrees Celsius to freeze. It also has a highly variable coefficient. Of expansion over its whole temperature range. 10 to 20 degrees Celsius, you must beta will be 0.15 of water, and that is the here temperature and the beta values, which will be the different at the different distance in the liquid. When you talk about solids, will be the constant. Now, and the Boyle's law. Boyle born in 1627, the 14 children of the Earl of Cork, discovered his law himself. He used a U-shaped glass tube, closed at one end, open at the other. He first carefully poured in a mercury with the tube almost horizontal, so the trapped air was at atmospheric pressure. The level in the two arms were equal. He then poured in 13-inch more of the mercury, that's 1 atmosphere, and found the trapped air now had half the original volume. This is the experimental diagram. That the volume Boyle's law. Boyle knew that fast compression hit gas. So before measuring the volume at the higher temperature, he waited for the air to cool back down. He repeated the experiment at a different air pressure. He found that at a constant temperature T, pressure and volume will be pressure. The product of pressure and volume will be the constant. As a constant, PV is equal to constant, and this is the relation between P and V, and is the graph, and this is experimental diagram. Expansion coefficients of a gases. Now you can see in expansion in the solid, then liquid, and now we're talking about the gases. Charles' law. At a century after Boyle and Charles discovered that a constant pressure and fare from liquefaction all gases have the same expansion coefficients. All gases have the same expansion coefficient. That means V at T degrees Celsius is equal to V at 0 degrees Celsius into 1 plus T over 100 273. This suggests the gas volume shrinks to 0 at minus 273, but of course it liquefies first. The Kelvin temperature scale T in a Kelvin is equal to T degrees Celsius plus 273.15. Here you can see the structures figures A and T in Celsius and also V proportional to T in a Kelvin. Now the ideal gas law, we combine the all laws, Boyle's, Charles, to find the V is equal proportional to T for gases well away from liquefaction. Note that this implies that at a constant value V proportional to T. The standard notation for this ideal gas law is V is equal to nRT, Charles, Boyle and Avogadro. Here we get an equation, the ideal gas equation, which is V is equal to nRT. Here N is the number of moles, R is the gas constant, universal gas constant, which value is 8.1314 joule per mole Kelvin, and T is the temperature, V is the value, and P as a pressure. Now the gas law exercise, you can see 100 liters of the oxygen at a 27 degrees Celsius and absolute pressure 10 atmospheric are compressed to the 15 liter. The gas is absolutely taken to 227 degrees Celsius. What is the final pressure? Here what you gain? First see what you gain. Here 100 liters of oxygen, that's the V1. T1 27 degrees Celsius, must you convert into the Kelvin. P1 10 atmosphere. Now it will be compressed. Now V2 15 milliliter and T2 177 degrees Celsius. What is the final pressure? P1 upon T1 is equal to P2 upon T2. So you get the P2 is equal to 13 atmosphere. This is the atmospheric is the unit of pressure. Now thank you for this.